let's talk more about derivatives. So if you have z as a function of both x and y, in Math 126 you learned how to find the partial derivative of z with respect to x and the partial derivative of z with respect to y. And what this meant was if you had a surface, just drawing that to make it look three-dimensional, if you pick a point on the surface and you walk in the direction of the x-axis, are we going up or down? So here we're going down, and if you walk in the direction of the y-axis, are we going up or down? So here we might be going up. It's hard to tell from the picture, but your calculations will certainly tell you. So there we could only go in two directions. So that seems kind of limiting. But we actually can go in any direction, or we will be able to in a couple minutes. So we pick a vector a comma b, and we might as well pick a unit vector, meaning a vector of length 1. Because if you pick one that's twice as big, you'll just be going the same amount up or down, but twice as much. So we're going to make all these unit vectors. So for example, the partial derivative with respect to x corresponds to the unit vector 1, 0. You're walking in the direction of 1, 0. How far up or down are you going? And partial derivative with respect to y corresponds to the unit vector 0, 1. But now we can do all sorts of unit vectors. So one I'm going to use pretty often is the vector 3/5, 4/5. Why this vector? Because it's cool that this is a unit vector. This comes from the friendly triangle that you hopefully learned in 10th grade, the 3, 4, 5 triangle, right angle triangle. So if we scale that down by a factor of 5, you get that unit vector. So that's a fun vector, and it's an easy one to calculate with because everything's rational. So we could walk in the direction 3/5, 4/5, so that's going to be somewhere between here. We can actually now walk in this direction and say, do we go up or down? And actually on this picture it looks like maybe we go neither up nor down. So we would expect the directional derivative in that direction to maybe be 0 at that point. Okay, so the notation, because we can't just use, and like before we had zx too, that was a different notation, and zy, but that notation's not going to be good enough. So we're going to use a capital D for derivative, and we're going to put the vector u, so u is some vector a comma b of the function f, and that's going to be notation for the directional derivative. Okay, and so one thing to note is that the directional derivative in the direction 1, 0 of f is just going to be the partial derivative of f with respect to x, and the directional derivative in the direction 0, 1 of f will be the partial derivative of f with respect to y. Okay, now how do we calculate these? Well, it's actually easy. The directional derivative in the direction AB of f is exactly what you would expect. It's a times fx plus b times fy. So that makes these formulas make sense. You can check those out, and you're just going, some fraction in the x direction and some other fraction in the y direction, and we have it's a unit vector, so we have a squared plus b squared has to be 1. That's what unit vector means. Okay, we've got some other notation. We're going to introduce the gradient. Gradient is just convenient notation. So if you have some function f in terms of x and y, we're going to put this upside down triangle. This is often pronounced del, or we say gradient. So the gradient of f, or the del of f, is this vector fx comma fy. And if you don't plug in a point, then those are still functions probably of x and y. Okay, and what the gradient tells you, just like colloquially, if we talk about climbing a mountain, the gradient might tell us about the steepness of the mountain. This is exactly what it tells you about the surface. Z equals f of xy. This is the steepness of the surface. Okay, then we can go back to this formula and write it a different way. So now the directional derivative, and this is just sometimes a convenient way of writing it. You don't have to do it this way. You can think of it as a linear combination of fx and fy. But you can also think of it as the gradient dotted with, or actually I'm going to write directional derivative of the vector u. Gradient dotted with the vector u. And dot product just means multiply the x's and multiply the y's and then add those products. So that's exactly what that formula says. So that's just kind of by coincidence. But what this formula allows us to do is it allows us to think about how big this directional derivative is. So we can think of that dot product as, remember from 126, this was the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, right? This was the scalar product, so this turns out to be a scalar. So the reason for doing this is to say that to maximize the directional derivative, we have to make the vector u go in the same direction as our gradient vector. Nope, not delta. Upside down is del. Same direction as our gradient vector. And then also note that because we made u a unit vector, then the magnitude of that is 1. So this is really magnitude of the gradient times cosine theta, and the maximum possible value of cosine theta is 1. So maximum magnitude of the directional derivative is actually going to be the same as the magnitude of the del function. That's how to maximize it, is we make theta basically 0. If we wanted to maximize it but going in the opposite direction, so make it as big as possible negatively, we just make u go in the negative direction of del, make theta pi basically. And then we can also minimize or make 0 by saying, by making u orthogonal to del of f, or perpendicular. That's making theta pi over 2 here, and then that would make that 0. And you learned that at 126, the dot product of two orthogonal vectors is 0. And this is what gives us what we call the level curves. So if you have some surface, I think you saw this in 126. Let's say you have a paraboloid like this. Then, and we even actually draw them in the picture. So if we're walking around these circles, we're not going up or down. Directional derivative, if it's positive, tells us we're going up. So like if we started here, directional derivative in that direction would mean going up. In this direction would mean going down. But if we go in this direction, we're not going up or down. So the level curves are curves on which the directional derivative is 0. So let's say that was the origin. That was 0, 0, comma, some value z. Let's just say it's 0, 0. I already used the letter A. Let's call it C. Then, I believe you saw these diagrams in 126. There's the level curve diagram for that paraboloid. Meaning, walking along those circles, you're staying on flat ground on the surface.